All right, let's talk about some other stuff. So good morning, everyone. So yesterday I ran into Corey on my way back from the gym, and she gave me a look that she really didn't like my gym outfit. So from that, bad intro. But anyways, I have group assignments for you this morning. So we'll start off with just some group assignments. Because Corey made me sad that she didn't like my outfit. So I'm going to give you guys 3 points. Basically, because of that. So anyways, we have 2 problems here. So the first one is, and then I have a third one after this one. So the first one says we have an ion source. It's produced from lithium ions, or lithium-6 in this case, which have a charge of +E and a mass which is 6 times that of the proton. So it says that the ions are accelerated by potential difference of 10 kilovolts and pass horizontally into a region where there is a uniform magnetic field of 1.2 Tesla. So what I want to know then is what is the smallest electric field that could be present to make sure that these guys pass through undeflected. So this is basically a velocity selector problem. So let's kind of draw the situation. So what's happening here is I have this potential region. So this is 10 kilovolts worth of potential. My electron starts inside of here and then is going to escape. So it has a velocity of v. And I'm going to send this guy through parallel plates where this is going to have an electric field, say, pointing downward, and a magnetic field pointing inward. So here what we know is that the magnetic field's magnitude is equal to, what was it, 1.2 Tesla. So from here we want to determine what is the electric field. So basically this section here, you're going to use what you used on the second exam, which is conservation of energy, to then determine what is the velocity at which it comes out. And then once it comes out with that velocity, you want to tune the electric field to make sure that these guys go through undeflected. So remember what we had in that case was that the velocity was equal to the electric field divided by the magnetic field. Which basically means that here, all you have to do is solve for the electric field then is equal to the velocity times the magnetic field. So here, use conservation of energy, change in kinetic plus change in potential is equal to 0 to find that velocity. So that's the first problem. Problem number 1. So let's take a look at the second problem. So the second problem says that we have a charged particle moves into this region of uniform magnetic field and goes through a half a circle, and it takes the time of 130 nanoseconds for this thing to go through a half a circle, and then come out. So the first thing I want to know is what is the magnitude then of the magnetic field to make sure that this thing does take 130 nanoseconds for this thing to go through half a circle. And then finally we want to know if it is sent through with, say, twice the amount of kinetic energy, how much time does it take to go through? So initially, this thing is moving through with some velocity v. It's going to pass through, go through with 130 nanoseconds to go through this half a circle. If I now give it twice the amount of kinetic energy, this thing is now going to go through a bigger circle and then come out. So the question is, how much time is it going to take? The answer is 130 nanoseconds. It's exactly the same. So I want you guys to show that to yourself and prove that to yourself that it is exactly the same. So what happens is even though the velocity is bigger, the radius becomes bigger, which means it has to cover a bigger amount of distance. So with a higher velocity, with a bigger distance, it takes exactly the same amount of time. So I want you to kind of prove to yourself that that's actually true. Okay. So for this one, the first thing you need to know is what type of particle is it? Is it a positive particle or is it a negative particle? Meaning is it a proton or is it an electron? The way you're going to do that is use the fact that here the velocity is going downward, here the magnetic field is coming out of the board. So use the right-hand rule then to determine is it a positively charged particle or a negatively charged particle. Once you know that, then you know the mass, and then from there you can then determine the magnetic field. So if this thing takes 130 nanoseconds to go through half a circle, how much time does it take for it to go through half a circle? What would we call that by definition? Half a period, that's right. So to go through a full circle, this thing would be a period. So this is going through half a circle, which means 130 nanoseconds is half of the period. And also remember that the period, if I get this right this time, so the period then is equal to 2m pi divided by the charge times the magnetic field. So this is the period. So in this case, what you know is that your 130 nanoseconds is equal to 1/2 of the period, which in this case then is equal to pi m divided by qt. So use this then to determine the magnetic field. But again, to determine the magnetic field, you need to know what's the mass. So the first thing you need to do is determine what type of particle is it. again, is Q positive, meaning that this is a proton, or is Q negative, meaning that this is an electron? Seems okay? I got one more for you. Let's bring up the next one. This one has to do with what we talked about yesterday, a loop of wire and an external magnetic field, which is magnetic torque. So basically what's happening here is I have 10 loops of wire, even though I only drew one, but I have 10. So imagine I have 10 of these guys stacked on top of each other. Is parallel to a uniform magnetic field. So basically what's happening here is, here's my loop of wire, my magnetic field is going in this direction, so the face of this is parallel to the field, which means the area vector is going to point in this direction. So this is my area vector. Dependent. From here, I have then 2 amps of currents running through this wire, and this guy is free to rotate about these 2 pivot points here. So basically this thing is, I'll use my cell phone this time, there's 2 pivot points here, so this thing is free to rotate something like this. Right? Now what's happening here is I'm putting a mass on this side, so this mass is then 50 grams, which is going to cause it to feel a torque in this direction and wants to rotate this way. But I want to run the current through it in such a way that this thing is going to rotate back in this direction due to the magnetic torque. So what I want to know then is, what is the strength of the magnetic field that I need, given that it has 2 amps worth of current, to have that this thing stays exactly stationary? Which means that I want the magnetic torque to equal the gravitational torque. So this is what we want to know. So in this case, we want to know, what is the magnetic field? So for the third problem, what's happening here then is I want the magnetic torque to then equal the gravitational torque. So the gravitational torque is going to be given by R cross the gravitational force, which is simply mg. So this is the gravitational torque. Remember the magnetic torque, as we talked about yesterday, is mu cross B. In both of these cases, the angle is simply going to be 90 degrees. So for both this one and this one, the angle will be 90 degrees. So that sine term is basically just going to go away. So good. So here, for the third one, you have to determine what R is. For the gravitational torque, R is this distance here. So it's half of the length of this guy, which is then going to be 2.5 centimeters. Because it's pivoted about the center. Okay? So, it's kind of a lot, so I'll give you about 20 minutes to kind of get started on those, and then we'll talk about the Hall effect, which will be the only thing we'll talk about today. We'll do an example of the Hall effect, and then I'll give you another group assignment corresponding to the Hall effect, and then while you're working on that one, I'll give back the thing that you may or may not want back. So, life will be good. So, let me bring up the first one. So these two, so you can kind of see these two again. Just to remind you of all the quantities. There we go. And I'll be walking around so you can ask questions and do all that stuff. Still feeling sad that Corey didn't like my outfit. I never saw that. The look on your face, give it one. She will not. I know that she looked at it like 6 times. Crowd in my office. So remember, for the first one, the way that the potential energy is related to the potential is, remember, change of potential energy is the charge times the change of potential. Get started on that one. Here, the charge is simply the fundamental charge, E, which is 1.602 times 10 to the minus 19 joules. And the mass is 6 times that of the proton. And remember, the mass of the proton is 1.67 times 10 to the minus 27 kilograms. 6 times. they're all constants. Okay. Can do what? Yes. Yeah. So that'd be 10,000 volts. Yeah. Yeah. So everything has to be in its fundamental units.
That's just like right? That's just like a change.
Yes, that's right. So the 10 kilovolts here is just delta. You're solving for the magnitude of electric field. Yeah. So here you're saying E is equal to V times P. So this, and then you know what E is, you just get there. After about 20 minutes, and then we'll do all that. And it's one more after. Cool. So first thing we want to do is start off with that conservation. So this one is going to be just the final minus the initial. Oh, good. So the delta V is just the 10,000. So this is going to go from a high potential to a low potential, which is the change of potential is actually negative of volts. So this is going to be minus 10,000. E. Well, I'm going to have a minus. I'm just going to pull minus out. Times fundamental. And that's all you do.
So it's 6 times.
Yeah, that's all that would be. Now, once you have that, that means the same as that. So that is all.
6 times.
What's up? Oh, so remember that a positive charge always goes from high potential to low potential. So that means that this thing is starting off in a potential of 10,000 volts and then going to, which means the final potential is 0, the initial potential is 10,000 kilovolts, which means the change of potential is actually negative 10,000. So I just have to make sure that's negative, otherwise I get an imaginary velocity, which is not.
Okay. So you end up with 1/2 m squared minus 10,000 E.
Correct. Equals 0. Exactly. Exactly. Or 1/2 mv squared is equal to E times 10,000 volts. Either way is fine.
Yeah.
Yeah. For the electric field, I think so. Yeah. What do you mean? 10 to like the 7th or so? Yeah, like 10 to the 6th. Yeah. I mean, that's a big potential.
Yeah, that's what I was thinking. Obviously, it should be pretty quick.
Yes.
Oh, don't forget your P. So this is just delta V, but the 2 times E is delta U. Oh, I think. So E is equal to 1.62 times 10 to the minus 19. M is, well, mass of the proton anyways, is 1.67 times 10 to the minus 27. So this mass would be 6 times. Yeah. So, what I did was I substituted and all. Oh, you're doing that. Okay. That's a good question. I'm not sure.
Oh, the electric field?
Right. So where does this lead? That is your field. Well, that's not true in this region. So this would just be delta. So change potential. So rewrite that as so that's a bit. So keep the Q there. 6.79. Yeah. What is the unit? So yeah. That's probably what the test was. Well, 200. Well, you know W, that's 10,000 volts. You build a ring out of it. I don't think velocity. I forgot velocity. So start here instead. And then once I solve it, you're not going to be the electric field. Well, that's just the electric field. So that's the electric field between them. Once I have that, then that's just so that should work. We're trying to do it now. But just remember delta V here. Right. It would be on proton. Well, the magnetic field's coming out. Right?
Oh, that's coming out. Okay.
So in that case, you put your fingers this way, curl this way, your thumb points like this. So it would be a positive. It would be volts per meter or
You just said volts, so it's Newton per volt.
yeah, Newton per coulomb or volt per.
Like it's volts. No. The Tesla was confused.
Newton per
Or Newton's per volt.
the way you.
You're always mad.
Oh, E times. Yeah, no, that's fine.
You know anything that in your head?
6 points. 1.602.
Times 10. You said big.
I would have thought it would have been by now. No problem. But it won't show up much for the physics.
That's just saying positive or negative, right? That's the
I mean, the only thing velocity downward. It's not out of the board. That's how it's going.
Yeah. I wasn't there. You're the one that big ER.
Not like you go faster than 3%.
It's
Like,
still
it's higher than that.
serious.
I don't want to
On the floor, cramping up. That's like he's getting work. Yeah.
Just saying it's fun.
Give it about 9 more minutes. All right. Talk about.
We're getting some chemistry stuff. I'm not like. Almost all of this is pretty much chemistry. You show me.
She can argue otherwise, especially when you do quantum mechanics.
I just don't want to ever have to do Newton this ever again in my life.
So bad.
Chemistry is the quantum mechanics of a single unpaired electron.
All I know that we use it for is conversions. That's what we do. I don't think we've used, I mean, we probably use some of the physics, but like, not knowing the, like, I don't know.
Right.
You want to tell them that? What did you get? Yeah, exactly.
Sure. Correct. Yeah. So it has to be. Of course, has to be.
How are like that?
Oh, so would you want?
Yeah, see, that's what I'm thinking.
So let's assume for now.
No, I didn't think of earlier.
So what's happening is look at the super portion where it's coming. The necklace, which is over.
I was just sitting up here like, yeah, no, where you got that from? It's almost got full.
So in this case, since it's curling in this direction, then my thumb always points in the same direction as the actual force does, so it has to be positive. But if it's curling in the opposite direction, where like that case is the block is this way, the force is this way, but the actual force is this direction. It means I have to rotate my hand by 180 degrees to get it to be the correct direction. So in that case, it would have to be a negative. So anytime I have to do that extra 180 degree rotating, that would make it a negative. Yeah, just always start off with the fact that it's positive. Just assume that it's positive, because that case your hand comes in the correct direction of the right hand. And then you compare the direction of your right thumb, that force direction, to the force. That's the same direction, that has the opposite direction.
What's the
The opposite direction, and then have a 180 degree rotation. It has to be.
But then we're using different.
Well, we're still using the same thing.
I thought for being this.
It's just we're comparing the direction of are some versus the direction of the actual. Okay. So we're using the gradient rule, comparing that to what we know about the direction.
So we're basically, is that target transfer?
Correct. If it doesn't, if it's 180 degrees there, then it has to be. So the actual force through this way, back on the force. And now we get here, here. How does this work? I can write that. What's up?
Oh, yeah, it's two.
This was actually
2 pi in.
Gosh dang it, Mitch. What?
It was over.
Yeah. So you have yeah, so if I double the kinetic energy, you got into the other the first two. But if I increase the velocity by 2, then I quadruple.
I just want to know how you got the answer. I'm just saying, well,
That's okay?
tell me what is the equation?
Well, this is half period. So for the actual period, it would be 2 pi n over 2.
I just wanted you to say that and not scream at me. Because I thought it would just be 2 pi n over q.
Yeah.
Because I didn't know there was an extra 2.
Equals 130. Or equal 130.
So is that 4 pi n over q?
See, yeah, so if I say 130 nanometers, then that would just be equal to pi n over 2. But that's half. So I want to compare correct. So if I want to compare that one full period, I would have to say 130 nanoseconds multiplied by 2. So 260 nanoseconds is the period. Okay, so I just multiply over 130. Yeah. That's right. So we're either saying 130 times 2, 260 nanoseconds is the period. Or now divide both sides by 2. So now 130 nanoseconds is half. So then we're just taking the equation of the period and dividing by 2.
So you're just saying we don't have to do anything.
No, I'm just saying that is half.
Where's the 4 coming
Yeah, here. Well, let's look at your numbers. Plus.
You just keep getting closer and closer. You're getting more extra comments.
So this is saying minus 27 plus 19 plus 9. Okay.
You gotta change the nanoseconds to seconds. That was pretty good.
It is a proton. It's just all right, so as I said, these are already up on Blackboard, so you can still work on these guys later. So let's talk about some new stuff. The only thing we're going to talk about today is what's called the Hall effect. So the nice, interesting thing about the Hall effect is that this was the experiment that told us Benjamin Franklin was actually wrong. So what Benjamin Franklin thought, and I talked about this before when I talked about the direction of currents, was that it was positive charges which were moving in a given direction. But this experiment actually is what showed definitively that that's not actually true. It's actually negative charges moving in the opposite direction. So what Benjamin Franklin thought is that current consisted, again, of positive charged particles moving, say, in this direction with a drift velocity v. And this guy is positive, but it turns out in reality, in that same wire, what's actually really happening is that we have negative charges moving in the opposite direction. But these two things cancel each other, which gives the current still in the same direction. Okay. So how did this actually work? Well, to do the Hall effect, we're going to do something kind of interesting. So let's talk about the Hall effect itself. So the Hall effect, we're going to take a piece of metal. So let's say here's a piece of metal. So this thing has a length and a width and a height to it. And we're going to put this in an external magnetic field. So let me say this is the x direction, this is the y direction, in the z direction. Pardon me. And then what I'm going to do is put this in an external magnetic field that, say, points along the z direction. So this is my external magnetic field. And then basically what we're going to do is we're going to run a current through it and see what happens. Okay. So let's assume for now that we go with Benjamin Franklin that these guys are actually positive charges. So here's my positive charges. These guys then are going to move with a velocity v, say, in this direction. But these guys are moving in an external magnetic field perpendicular to the external magnetic field, which means they have to feel a force. So our right-hand rule tells us that if the x direction is this way, I point my fingers in the direction of the velocity. But my magnetic field is upwards, I got to rotate my palm, curl towards the external magnetic field. So my thumb is going to point in this direction. So this thing is going to feel a force in the then negative x direction. So this is going to be, or sorry, negative y direction. So this is going to be the magnetic force then on the charged particles. So what happened then is what? As these guys are moving, because my current, in this case, is again moving in this direction. So this is the direction of my current. As these charged particles are moving in the direction of the velocity, which is in the direction of the current, they're going to feel a force bringing it to the negative y side of the metal, which means all my positive charges then are going to start to build up on this side of the wall. Okay with this? So what happened then is because of this force, on this side of the metal, I'm now going to start building up positive charges. All these positive charges will be pushed in the negative y direction, so they're all going to be built up on this side. But if all my positive charges are getting pushed this way, what builds up on this side? Electrons, negative charges. So what happen then simultaneously is I have to then build up negative charges on this side, which means what? Now I have positive charges on this side, negative charges on this side. What does that create? An electric field. Okay. So now what we have is on the inside, we build up an electric field on the interior. Now what I have is a positive charged particle moving in an external electric field now. What does that feel? That also feels a force. But in this case, since it's a positive charge, it's going to feel a force in exactly the same direction as the electric field, which means that it's going to feel a magnetic force in the negative y direction, feel an electric force then in the positive y direction. So this thing is now going to feel, let me use that in gray, an electric force in this direction. So as these guys start to move, I'm going to build up positive charges on this side, negative charges on this side, create an electric field on the interior, which means as more positive charges go on this side, more negative charges go on this side, the electric field will get bigger and bigger and bigger and bigger and bigger, until eventually what's going to happen? Well, eventually what's going to happen is that the magnetic force is going to equal that of the electric force, which means that these particles will no longer be deflected. They're only going to move through the wire in a straight line. Okay? So what will eventually happen in the Hall effect is that the electric field will eventually equal that, or the electric force will equal that of the magnetic force. These two things will be equal and opposite to each other. So from here, we know that's what? The electric force is simply the charge times the electric field. The magnetic force then is going to be Q times B times sine of the angle between the two. But if my velocity is pointing in this direction, and my magnetic force points this direction, what's the angle between the two? 90 sine of 90 is simply equal to 1. So I get QE then is equal to QVB. The Q's are the same. It's the same charge moving, so those guys are going to cancel. So what this says then is that I have the electric field then is equal to the velocity, or the drift velocity, times the magnetic field, which means that the drift velocity then is equal to simply the ratio of the electric field to the magnetic field. Same thing we found in a velocity selector. Now, what eventually tells us that it was positive charges versus negative charges is if I have an electric field across these plates, I also have a potential difference. So across these plates is then a potential difference, delta V, which is what's known as the Hall EMF. So this is equal to the Hall EMF. So what happens is by simply putting these charges into an external magnetic field and then running a current through it, I'm creating an electric field, which also creates a potential difference, which is what's called the Hall potential. Now, to measure the Hall potential, what we also know is what? If this thing has a, let's call this width, W, then the electric field is related to the Hall EMF by the width. So from here, what I can do is I can actually rewrite this as the Hall EMF divided by the width is equal to the velocity times the external magnetic field, which means the Hall EMF then is equal to the velocity times the width times the external magnetic field. This is what's called the Hall EMF. So what's interesting here is that by simply applying an external magnetic field, we create a potential, we create an electric field, and we can measure that potential. Now, here is where we determine what was positive and what is negative. So what you can do then is by measuring, putting your negative probe on this side and your positive probe on this side, if it's positive charges which are actually moving, again, you should get positive on this side, negative on this side. So if you put your negative probe on this side, positive probe on this side, you should measure a positive potential difference. But that's not what we measured. What you measure is that it actually turns out to be a negative potential difference, which means that it's actually negative charges on this side and positive charges on this side. The complete opposite of what you would expect if it was positive charges moving. So what that means, what's actually really happening is that there are negative charges moving in the opposite direction. So in that case, I would then build up negative charges on this side, positive charges on this side, to then tell me what is actually moving within inside of this material. So this was actually the Hall effect. This is what actually told us that it's negative charges which are actually moving throughout a wire, not positive charges, by simply looking at the force on these charged particles, given the fact that you get a charge separation, which creates a dipole moment, which creates an electric field, which creates an EMF. By measuring that EMF, you can then determine if it's positive or negative charges. So this is the Hall effect. So Hall effect simply says that if I put these charged particles in here, in an external magnetic field, I'm going to create a potential difference. The potential difference is given by the velocity or the drift velocity at which they're moving, times the width, times the external magnetic field magnitude. So let's do an example. This is problems. Nope, not potential. 1, 2, 4. There we go. 6 maybe? No, 7. Good. So this says we have a long copper strip, which is 1.8 centimeters wide and 1 millimeter thick, is placed in an external magnetic field of magnitude 1.2 Tesla. A steady current of 15 amps is then run through it. The Hall effect, or the Hall EMF, is measured to be 1.02 microvolts. So now I want to know, determine the drift velocity of the electrons and the density of the free conducting electrons inside of the copper. So let's draw our picture. So all this says is I have this strip of metal. Here's my strip of metal. This thing has a length, a width, and a thickness to it. I'm going to put an external magnetic field perpendicular to this guy. So this is my B field. and we have a current running, say, in this direction, I, where I was equal to 15 amps. Let's put in all the other quantities. So magnetic field is 1.2 Teslas. Put that guy in. This is 1.2 Tesla. And this thing has a width to it and a length. So let's talk about the length first. So this is the length, L. And this guy here is the width, W. So we're told the width and the length. The width in this case, oh, also the thickness. So the thickness is this direction. So that's our thickness. Let's call that little t and the thickness. Good. So here we're told that the length is 1.8. The width is 1 millimeter, or that's the thickness. Oh, that's wide. Okay, 1.8 width and 1 millimeter wide. So width is, this is thickness 1 millimeter, and this was what, 1 centimeter? I already forgot. 1.8. Okay. There we go. Centimeters. And then what it also says is that we measure potential difference across here, this Hall potential, which is 1.02 microvolts. So that's that guy. Did it tell you the length? No, okay. We don't care about the length anyways. Okay, it was okay? Good, so part one, or part A, or the first part is then asking for, what is the velocity? So what's the velocity equal to? So what's the drift velocity at which these guys are moving through? Well, we now know that the Hall EMF is equal to what? The velocity times the width times the external magnetic field. So here, this says then that the velocity then must be equal to the Hall EMF divided by the width divided by the external magnetic field. So this is my velocity. So this is 1.02 times 10 to the minus 6 volts divided by the width, which is 0.018 meters, times the external magnetic field, which is 1.2 Tesla. Plug in our numbers. What we find in this case then is that the velocity works out to be 4.7 times 10 to the minus 5 meters per second. So this is the drift velocity, or the velocity or the speed at which the conducting electrons are actually moving through. Okay? The next part then says, okay, what then is the number density, N? So how can we then relate to the number density? Well, let's think about what we knew on the last exam. What we know is that the current is equal to the charge times the number density times the area times the drift velocity, or the current density is equal to the charge times the number density times the drift velocity. Either one of these two will be sufficient. In our case, we know exactly what the current is that's given in the problem. We know the geometry, so we also know the area. We now know the drift velocity. That's the same thing we just solved for in the previous part. We know the charge. The charge is the fundamental charge because there are electrons which are moving. So let's use the first one here to solve for N. So this then says that N is equal to what? The current divided by the charge, which is the fundamental charge, times the area times then the drift velocity. The area here is simply the area which the current is flowing through. So the area that we care about is this cross-sectional area here. This is the area that we care about. This is the area which the current is flowing through. So here, since we know the width and we also know the thickness, and the area is simply the width times the thickness. So this is then going to be equal to the current divided by the fundamental charge times the width times the thickness times that velocity we found in the previous part. So plug in my numbers. What I find in this case then is that there are 11 times 10 to the positive 28 per meter cubed. So there's 11 times 10 to the 28 conducting electrons per meter cubed. So this is my number density. My Hall effect. Okay? So that's about it. That's all I want to do for that one. So that brings up one more group assignment for us. These are online examples. Workshop. There we go. So this one says, in the Hall effect experiment, we have a current of 3 amps runs lengthwise through a conductor, which is 1 centimeter wide, 4 centimeters long, and 10 microns thick. So remember, micron is micrometer, which is 10 to the minus 6 meters. It says we have a Hall potential difference of 10 microvolts when it's placed in an external magnetic field of 1.5 Tesla, passing perpendicularly through the thickness. So the first part is, what is the drift velocity of the charges? And the second part is, what is the number density? This is exactly the same problem we just did. It just has different numbers. This is your group assignment. Do exactly the same thing, just split in different numbers and come up with new numbers. That's it. I'll let you guys go to work on that while I pass out this exam thing here. Goes back to you guys. I still have to grade the extra credits, but I did grade the extra credit that was on the exam. But wasn't quite as good as I had wanted, but you know, these things happen. Wasn't too bad. So turned out on this one, the average was about a 62. So I like to have seen it a little higher, but that's these things happen. So, having said that, the highest was a 92, and I think the lowest was like a 31, so not too bad. But anyways, I'll hand these things back, and I'll let you guys work on those, ask questions, take out the garbage can. Go. Yes. 10 to the minus 6 meters. So a micron is a micrometer. I like your joke, by the way. No, Molly did.
I guess,
How does a physicist medical bills? Put a whole bunch of negatives there. I don't know, is it? All right, so I'll see everybody tomorrow. So tomorrow we're going to start working on how do we actually calculate magnetic fields. So basically we're going to start off with the equivalent of Coulomb's law for the calculation of magnetic fields, and then move into the equivalent of Gauss's law. So tomorrow we get to start all that. Do you think?
how much were the short problems?
13 each. Yeah. Yeah, last semester I think there were 15 each. So yeah, this semester there were 13 each. Oh, in this case, so it tells you that it's going, this is a transverse Hall potential across the width. So since that's across the width, then they have to be moving lengthwise.
Okay.
Which means in this case, the area you care about is the same one we had before. It's just the width times the thickness.
So they just give us the next.
I just gave you the length just because to throw you off.
Wait. So we don't need the-
You don't need a length at all. You don't need that 4 centimeters. So the area in this case is just